Over 100 years ago, it was noticed that a counter movement produced a higher jump than when a counter movement was not used. A counter movement is a movement in the opposite direction to the goal direction. And this was initially called the wind-up movement, and in 1979 it was renamed the stretch-shortening cycle. The stretch-shortening cycle occurs when the active muscle is first lengthened, which is called an eccentric contraction, immediately before shortening, and this shortening is called the concentric contraction. Several possible explanations are given for this stretch-shortening cycle effect on force production. And the first is motor units and muscles work more effectively with the pre-stretch, and therefore more power is produced. The second reason is that a counter movement permits time for the central nervous system to fully activate the sarcomere contractile machinery. The third reason, the elastic protein woven throughout the muscle fiber and the tendon stores energy during the eccentric contraction phase and then reuses that energy during the concentric contraction phase. And the muscle spindle stretch occurring during the counter movement triggers spinal reflexes that increase the muscle contraction to a level above what is possible when no pre-stretch occurs. And finally, the pre-stretch of the active muscle potentially alters the properties of the sarcomere's contractile machinery, and this will enhance the force produced. This enhancement is called potentiation and increases with the speed of pre-stretch. The word potentiation describes the enhancement of one agent by another so that the combined effect is greater than the sum of the effect of each agent by itself. And it's a word that's commonly used to describe the interaction between two or more drugs. In our case, the word has been stolen from the drug industry, so to speak, and used in reference to the interaction between the stretch of the tendon and the enhanced force outcome. The stretch-shortening cycle is particularly useful for storing energy in a tendon that in turn enhances the maximal force production, and we've talked a little bit about this already. Energy stored in the stretched Achilles tendon, for example, permits jumpers to produce a higher force at takeoff. Throwers use the elastic tissue woven into their chest and shoulder muscles by pre-stretching the relevant muscles just before final implement delivery. And a highly developed and effective stretch-shortening cycle in the quadriceps muscles improves the athlete's reactive leg strength by stiffening the touchdown leg. Athletes with a stiffer leg can run faster, jump higher or longer due to the shorter ground reaction time. One theory about the value of plyometric training is that it teaches the brain how to quickly recruit the fast type 2 fibers. Another theory is that plyometric training teaches the brain how to better predict the force of landing, enabling it to set up the relevant muscles into a higher level of pre-activity before the foot touches the ground. If you've ever encountered an unexpected step down and your knee gave way, it is because the brain was not prepared to stimulate the required muscular force to stop the knee from collapsing due to the force of gravity. And the idea that the brain learns to pre-tense relevant muscles before the foot strikes the ground comes from drop jump studies. Athletes who have the highest jump after they drop off a bench also have a very active vastus lateralis muscle before ground contact. Now here's a graph that is based on the data from this particular study. The green line is the activity of the vastus lateralis muscle during the highest jumps, and the black line is the activity of vastus lateralis muscle during the poorest jumps. And here is the point of touchdown, and this is the takeoff point. And as you can see here with this little arrow, that the vastus lateralis muscle was quite active well before touchdown when the jumps were very high, and had a lower activity when the jumps were quite low. Vastus lateralis muscle is also much higher in its activity throughout the ground contact phase for those subjects who had the highest jumps. The active vastus lateralis muscle has the effect of stiffening the leg, and this results in a fast stretch reflex that in turn results in a higher jump. The stretch shortening cycle is also important for helping accelerate limbs when there is no contact with the ground. When clearing a hurdle, for example, the hip flexor stretch reflex is thought to help accelerate the leg through for the next stride. Another example is a long jumper who also uses the hip flexor stretch reflex for a powerful swing leg at takeoff. The shot, discus, and javelin thrower use the stretch reflex in the chest muscles to accelerate the arm during the final delivery phase. In all these cases shown here, the limbs are not physically connected to the ground, and the stretch reflex serves to magnify the natural force of the muscle.